All right, welcome back from the lunch break. So let's now continue with the final lecture of the series on how to get the grand finale with the promised probabilistically checkable proofs and delegation of computation. So let's just recall quickly what we had in the last lecture. So we completed the near linear time toolkit for computing with univariate polynomials with basically the fast extended Euclidean algorithm and also Gauss decoder for Reed-Solomon codes that runs in near linear time. So in this lecture, we can now benefit from the entire toolbox basically. So we know how to multiply fast, how to divide fast, how to do fast batch evaluation, how to interpolate fast in the error-free case, how to do an extended Euclidean algorithm or greatest common divisor computation, if you will, and also how to interpolate in the presence of a modest amount of errors. So we have quite a strong toolbox, and what we want to do in terms of how to apply this toolbox is that, we already encountered uncertainty in computation in the sense that we now know how to, for example, protect static data using a powerful family of error-correcting codes called Reed-Solomon codes. Now let's try to advance a little bit further. So instead of protecting static data, so let's think about whether we could actually design proof systems in the fine-grained sense that actually cope with a limited amount of errors in computation. And of course the motivation is somehow, as we already encountered during lecture 1, is to be able to delegate computation. Again, this sort of slightly asymmetric setting that you potentially have a relatively weak computational entity, namely, let's think of your laptop or something like this, with modest resources that is reliable. So you can sort of trust that it gets the computation right. Whereas then there's the service providing party that is somehow a massive computational infrastructure, if you will, maybe a supercomputer, maybe some kind of data center and whatnot. So it usually has massive parallel resources in the vector parallel sense, especially if you're working with GPU, so single instruction, multiple data, or SIMD, if you like. And of course, with physically massive infrastructure, you also start potentially getting errors there, which also may be silent errors, that your computer simply doesn't crash, but it sort of makes an error without sort of raising a fuss about it. So this can happen. So then, of course, we get these questions that, okay, for example, if we submit a big computation to the cluster or the cloud, if you will, and we get as an answer, no, can we trust this? Because there are many programs that produce the answer no, and it might be that the desired computation was in fact not executed. So somehow, of course, this brings rise to the notion of a proof and maybe a proof system that the service provider is maybe supposed to prove to us using some means that the answer actually is no for whatever problem we are looking at. And then, of course, on the service provider side of things, if the hardware is unreliable, we would still like to provide reliable service. So how to do that? And then, of course, there's also the fact that once we have invested massive resources into the computation, and if the answer is no, and the client is not willing to pay, so how do we convince, let's say, a third party that actually the computation was executed? So somehow the proof needs to be transferable, that we can take it to the judge and insist that maybe we need our payment because we put the resources in. So there are many dimensions to this type of situation, but let's see whether we can sort of design something that would at least be partially satisfactory in such a setting, at least for specific problems, not necessarily for arbitrary computations, but let's say some highly expressive problems potentially. Okay, so here's the roadmap. So basically, as it turns out, so we are going to be looking at yet further application of the evaluation interpolation duality, and in fact for univariate polynomials, which is nice because this is what we've been sort of building for the previous 4 lectures. There are some exercises that sort of take this identity testing, review standard applications of it. Let's see whether we have time to actually look at the problem set, how you, for example, test that 2 polynomials are identical, or whether the, let's say, third polynomial is the product of the first two polynomials without actually executing the multiplication, or let's say, how do you check that the matrix multiplication has been executed correctly? So there are many classical examples of so-called polynomial identity testing and related randomized algorithms that are in the problem set. But what we would like to do is to maybe get a little bit more advanced and look at, for example, let's say the propositional satisfiability problem and how to design proof systems for that, courtesy of Williams. So we review one of Ryan Williams's proof systems. But before that, of course, let's try to make a little bit more formal as to what we mean by a proof system, what we mean by the proof system being complete and sound, and then, of course, if we sort of sacrifice a little bit on the soundness part of the system, that we only insist on probabilistic soundness and not a fully deterministic system. And also, there are sort of two players to the game in a proof system. So there's, of course, the act of preparing a proof, which, of course, most mathematicians know might be a tedious process, so it consumes a little bit of computational resources. And then, of course, there's the cost of verifying a proof. And, of course, ideally, we would like that the verification is substantially easier than preparing the proof. Again, thinking of this setup. So you run on a small box, you want to be able to verify here, and potentially you put a lot more resources to preparing the proof. But, of course, the proof preparation also needs to be somehow efficient in the sense that it shouldn't be much more expensive than actually solving the problem. Otherwise, it's probably a useless system. So that's the ideal. And yeah, we look at one of Ryan Williams's proof systems and see what kind of properties it has, and then some of our extensions of that. Basically, when we started with Andreas Björklund looking at what happens on the prover side of things and whether we could actually tolerate some errors in proof preparation. And again, since Ryan's wonderful system is essentially based on univariate polynomials, so it sort of amounts to looking at the standard Reed-Solomon decoding algorithms that we already saw, and then we actually get limited error tolerance in the proof preparation, which can take place in parallel. And there are sort of many features to potentially like about the system, but unfortunately it's not yet, let's say, for universal computation. So we can access many expressive computational problems, such as number CNF SAT, which we will define in detail shortly, but we don't yet have a universal system. And there's, of course, so let's get maybe started with the basic definitions, and I'll keep this at a relatively high level just so that we understand what's going on. So usually proofs involve some kind of claim, if you will, a problem instance that we would like to solve, and then that instance has basically either it's true or it's false. I mean, you make some kind of statement, and then the question is whether that statement is true or not. And let's assume that these claims are somehow computationally tractable, that there is actually an algorithm that, given an instance I, actually decides whether it's true or not. So that algorithm, after running for some time, potentially a very long time, decides whether I is true or false, and then gives that output correctly. And of course, what we would like to do is to somehow ease this effort, that maybe there is some extra information that we call a proof pi for the instance I that somehow makes things easier, though we don't yet necessarily require that. But the proof system basically consists of a verification algorithm, which we call the verifier V, that takes as input, of course, the claim that we want to check, together with something that is claimed to be a proof. Notice it's a pi tilde, not pi, so it may or may not be correct. And then the verifier is supposed to basically either accept or reject this pi tilde as a proof for the claim I. And of course, now we need to put some requirements what the verifier needs to satisfy so that this is actually a proper proof system. But this is basically the setup that we will be looking at. So there are two things that usually you want out of a proof system, namely completeness and soundness. So a proof system with a verifier V, we say that it's complete if for every true instance, actually, a claim that is really true, as given by the decision algorithm, so there is actually a proof pi such that the verifier accepts, given as input, the instance and the proof. That hopefully the proof somehow eases the act of verifying I. Okay, so completeness is important, that we can give proofs about the true things. But then, of course, I mean, there's a other side of the coin, that if the claim happens to be false, that is not true. So then actually, if the proof system is sound, it needs to be the case that no matter what we submit as a putative proof, whatever bogus stuff you give, the verifier will always reject on when given as input the instance and the alleged proof. So you almost must reject any string that you get as an alleged proof if the instance is false. So these are the things that you typically want out of a proof system. So let's relax. Yes?
So here we assume that there is no randomness.
Yes, that is coming on the next slide. So indeed, so this is sort of perfect completeness, perfect soundness. So it's a deterministic system. But now let's introduce a hint of imperfectness into the setting. So here we go. So now we relax from perfect soundness to probabilistic soundness. So now we have a proof system, and the verifier is now a randomized algorithm. So it has access to sort of unbiased independent random bits that it may use as it pleases. And now it's probabilistically sound if for every, again, input I and every putative proof that it gets, we actually will reject, not with perfectness, but with high probability, where this probability is taken over the randomness consumed by the verifier. So basically with probability 1 minus little o of 1, if you want, what is the definition of high probability in this case. And of course, usually these instances have some kind of size measure, such as the length of the claim in bits that we use to actually look at the asymptotic scaling of this. So now we have introduced a little bit of imperfectness. So it is possible if somehow the coin tosses that the verifier makes land in a very bad way, that we will actually accept a bad proof. But it only happens with small probability taken over the coin tosses of the verifier. Okay, so now we have proof systems, completeness. So maybe we insist still on perfect completeness. So if we get submitted a correct proof, we need to accept it with probability 1. But let's sacrifice a little bit on the soundness. And this is somehow what we start looking at. Okay, yes?
Does someone consider probabilistic completeness?
Yeah, I believe there are also such considerations. But let's just restrict. I mean, it's a large area, so let's keep with this. Okay, and usually, of course, what we want is some kind of notion of efficiency. So in addition to completeness and soundness, potentially probabilistic soundness, so usually what we want is efficiency. And here I'm sort of being efficient in a rather hand-wavy way, so I'm not going to go into quantitative terms until we actually have a concrete problem and a concrete proof system for it. Then we actually go quantitative. Here I'm just saying that actually the verification on input I and then a putative proof given together with I should consume somehow less resources than actually running the decision algorithm that we know exists by our assumption without any access to any kind of proof, because otherwise, of course, this is a rather useless exercise. So somehow this verification should be more efficient in terms of the resources consumed than, let's say, solving the instance from scratch. And again, maybe the benchmark here is somehow the best known algorithm that we can use to decide I, whatever that may be. And we will see one example of this. Yeah.
It also constrains the length of pi.
Correct. Yeah, indeed, tacitly. But again, let's not get too quantitative on this yet. Okay, very good. And then, of course, I mean, the verifier needs to be efficient, and maybe if we still want to impose further sort of design constraints or goals that we would like to have, is that we want to think about how difficult it is to prepare the proof, for example. So how much resources does an algorithm P, which we call the prover, actually consume when it sort of prepares a proof? And of course now, I mean, the prover gets a claim as input, and maybe it sort of needs to decide whether the claim is true first. And if it is true, so then it also needs to output a proof that is good for the verifier, in the sense that given the proof and the instance, the verifier will always accept if we assume perfect completeness. And again, what does it mean to be efficient here? What is the ideal thing is that somehow the proof preparation again, shouldn't take too much more resources than actually deciding I. So maybe there's a little bit of overhead, some kind of log factor or something, but sort of manifestly and in spirit, sort of not too much extra compared with deciding things. So that would be the goal. Okay, so we have what? We have perfect completeness, probabilistic soundness, efficiency on the verification side of things, and hopefully efficiency on the prover side of things. So these would be things that we would like to have, ideally, out of a proof system. So the area of fine-grained proof systems and, let's say, delegating computation has a lot of prior work as well. So I'm not going to survey these things in detail. So for example, if you just want correctness proofs, so there are sort of certifiable algorithms. There's a fantastic survey by Kurt Melhorn and collaborators on those. Then there's sort of delegating computation through interactive proofs, direction where you actually allow interaction between the prover and the verifier, started by Goldwasser, Kala, and Rothblum. Then there's sort of verifying computations without re-executing them, but not necessarily with tolerance for errors, so surveyed nicely by Walfish and Bloomberg. And these sort of in general aim at capturing arbitrary computation. I mean, or let's say relatively general families of circuits, if not completely arbitrary cases. Whereas then there's sort of one trend of research that I'm going to sort of look at in a little bit more detail, where actually people look at specific problems. Let's say number CNF SAT, three-sum, orthogonal vectors, closest vectors, and various other settings, let's say counting k-clicks in a graph and whatnot. And there you really, of course, have a state-of-the-art algorithm against which you can measure the proof preparation and, of course, the proof verification, and hopefully get some non-trivial results along this research. So again, it's a broad area, so I'm not giving you an exhaustive survey here. These articles that I cite are available in the references, so you can find more there and read further up on the area. So for purposes of this lecture, we will be actually looking at Ryan Williams's proof system for number CNF SAT. So we see what can be done in that case. So of course, for that we need to first recall the problem and then sort of start developing technology based on, surprise, surprise, polynomials. So, okay. Very good. So let's look at the Boolean satisfiability problem. I'm sure that everybody in the audience is already familiar with this, but let's just at least look at the notational conventions, what we are going to be using and how the instances look like. So x1 through xn, so let's let them be formal indeterminates that of course in general take values in 0, 1, meaning false and true as usual, but of course we may want to extend this to an arbitrary field eventually. So what is a truth assignment? Well, it's a mapping that assigns a value in, again, false or true to each of our variables here. So what is a literal if we start building an instance? So it's a variable or it's negation. So notationally you see the little bar there, so that indicates, the variable negated. So how do we define satisfiability? So what it means to satisfy a particular formula such as a literal. So it's satisfied in the positive sense if a truth assignment assigns the sort of true value to it, and of course in the negative sense if it's assigned a false value, as we know. And a clause is a set of literals, so variables or their negations. And we say that the clause is satisfied by truth assignment if at least one literal in the clause, viewed as a set, of course, is satisfied by the assignment. And then, of course, a collection of clauses is satisfied by an assignment if the assignment actually satisfies every clause in the set. So every single one of those needs to be satisfied by A. And we use C1 through Cm for the M clauses. So an instance typically has n variables and M clauses. Okay, so what is the CNF satisfiability problem, or if you will, the conjunctive normal form satisfiability problem in a little bit more formal setting? So the problem asks if we are given a collection of clauses, M clauses over n variables as input, whether there is a satisfying truth assignment that basically satisfies all the clauses in the aforementioned sense. Of course, we know, courtesy of standard complexity theory, that CNF SAT is an NP-complete problem, so we don't actually expect an algorithm that runs in worst case polynomial time in the length of the input in its standard binary encoding. And then there's a counting version to this problem, which we call number CNF-SAT, that actually asks for the number of satisfying truth assignments. Of course, it may be 0, but it can also be positive. And number CNF-SAT is number P complete, so it's as hard as sort of the counting problems in the class number P come. I'm not sort of going into detail into how one defines number P. So if you know the class, you know. If you don't, so then you need to read up on it. Okay, and let's recall the state-of-the-art algorithmics at that sort of the exponential granularity. So it's actually not known how to solve CNF-SAT. So even the decision problem, the decision version of the problem in time that would be a little bit below 2 in terms of the base of the exponential in the number of variables. So the standard exhaustive search where you try out all the truth assignments obviously runs in order 2 to the n time, where this star here means that we are suppressing a multiplicative polynomial factor in the input size, so namely in the size of the encoding of the instance. So this is the state of the art, basically, if you just look at the exponential growth rate. Of course, you can save a little bit on this in terms of sort of sub-exponential scaling, but that's the best what is known. So now, of course, I mean, this places a sort of curious setting to our hands. So could we potentially design, let's say, a proof system where the proof preparation would essentially take this time, but then we could, for example, produce proofs that enable us to, let's say, decide number CNF-SAT correctly. Maybe there's probabilistic soundness there, so there's a small probability of error, but maybe we could do the verification, let's say, in this time. Or maybe, in fact, in 2 to the n over 2 time. And this is actually possible, thanks to Ryan Williams's work. So that's what we want to start reviewing. But before that, so again, sort of, let's just recall the basics in terms of what we can prove easily and what is perhaps less easy to, once you start thinking about what we can do. So of course, I mean, if we want to prove that the decision problem is satisfiable, then it's very easy to give the satisfying assignment, and that is your proof, and it can be easily checked that every clause is satisfied by the assignment, and we are done. So this is sort of follows essentially by the definition of the class NP. That's what you have. But if you think about the counting problem, so then we get into a little bit more trouble. I mean, just to begin with, so how do we convince a verifier that a given instance is actually no satisfying assignments at all? So how do we prove that it's not satisfiable, let alone that there are exactly, I don't know, 1,000,001 satisfying assignments? So this means somehow that it's less easy, at least intuitively. Whereas giving an individual satisfying assignment is straightforward. Okay, so here is sort of, if you want to state at a high level, basically how Ryan's result looks. So this only looks at the verifier, so we will eventually look at the prover once we understand how the proof system works. But let's stare at the verifier. So there exists a randomized algorithm V, which we might just as well call the verifier, such that basically for all collections of m clauses over n variables and all integers capital N, so this is sort of the putative number of satisfying assignments, we have essentially the completeness and soundness properties. So let's see. So if it's the case actually that C has exactly n satisfying truth assignments, so then there is a bit string called pi, I mean proof, if you will again, of this length. So notice that it's about the square root of 2 to the n. So this is substantially less than 2 to the n in general, in fact exponentially less. Such that the verifier happily accepts this triple given to it, in fact, with probability 1. So it's deterministic. So you get a correct proof, you accept it. End of story. And then there's the sort of soundness case. So if the collection of clauses does not have exactly n satisfying truth assignments, so even if you're off by 1, so then basically for every bit string that you would like to give to the algorithm, no matter how long or how short, it's actually the case that the verifier rejects the triple with probability that tends to 1 as n tends to infinity. So And furthermore, so we run manifestly faster than the fastest known decision algorithm, which was 2 to the n, basically. So this is square root of 2 to the n, so exponentially faster. Okay.
How much time it takes to construct pi?
Yes, that we will get to eventually. But it's, again, O star 2 to the n. But, yeah. Yeah?
Like, if we could construct pi in this time, then we could solve that in this time.
Yeah, but we can. O star 2 to the n. I mean, that gives you enough time to go through all the truth assignments, and then the star hides this input size dependence. So we can definitely do this.
Like in this time, 2 power n divided by...
No. Yeah, 2 to the n, I said, for the proof construction time. Yeah. Of course, it would be a major breakthrough if we could actually solve that in 2 to the n over 2, but this I'm not claiming. I'm claiming that the proof preparation takes 2 to the n. And for this system, so given the input here in the correct case, so you can produce a proof for it. Okay, but I think we understand what is being claimed here. So now let's try to develop the proof system. And well, okay, now we get to polynomials, and we start with a polynomial that actually has multiple variables. So now we are a little bit outside of the box, in the sense that we actually view our, if you will, initially Boolean variables now with a little bit extended domain. So pick your favorite finite field with Q elements. So let's actually use prime order fields. So Q is a prime that is large enough that we will sort of soon constrain in more precise terms. So x1 through xn should be viewed as formal indeterminates taking values over the field. Okay, and then of course now we have a multivariate polynomial ring, so that's the notation, so let's keep that in mind. And what we will do is we will just sort of systematically algebraize the problem without yet sort of paying too much attention to any kind of computational cost or whatnot. So let's just present definitions and then start thinking about the computational complexity later. So just, so what we want is a polynomial, basically defined based on the collection of clauses. So we get as input a collection of m clauses that has the following property, that if I actually pick 0, 1 values to the variables, I mean alpha 1 through alpha n, which are in 0, 1, obviously it's a field, so it has an additive identity and a multiplicative identity which are distinct. Then we have that this polynomial assumes the value 1 if and only if the truth assignment A, defined by the obvious assignment, putting those alpha values into a truth assignment, actually satisfies the collection of clauses. And otherwise, we get a 0. So it's basically an indicator polynomial for the satisfiability of a particular assignment, as long as we work with 0, 1 values. Of course, we have the entire field here, so we will make use of that, but not yet. Okay, those are the constraints, so let's just sort of proceed with the step-by-step definition. So remember that clause consisted of, or a collection of clauses, of course, consists of clauses, and a clause consists of literals. So we start from the bottom, that we define basically polynomials associated with literals, and then go on from there. So again, in the straightforward manner, that's what you would expect. So if I have a literal L, remember it's either a variable or its negation. So let's define a polynomial in the variables associated with that. Notice it's basically if the literal is positive, namely the variable itself, so then it's 1 minus the variable, and otherwise if the literal is negated, so let's take the variable itself. So again, we can verify that this polynomial has the property that basically it assumes the value 0 if and only if, again, the assignment satisfies the literal, and if not, then we get the value 1. So it's basically complementary for the purpose that we want to use this to define closed polynomials, which we will do on the next slide. Okay, so what we do now is that we have a clause consisting of positive and negative literals, so it's a set of literals, and we want to define again a corresponding multivariate polynomial. So then it's defined in the obvious sense that you take 1 minus the product of the literal polynomials. Okay, so what does that mean if you think about it? So if the literal was unsatisfied, so then you got the value 0, and if it was, the that I got this right. So if the literal was actually satisfied by the assignment, you get the value 0, and if it was unsatisfied, you get the value 1. So let's think about what does this expression evaluate to if the clause is actually satisfied. So if there's at least one satisfied literal. So then of course we get at least 1 0 in this product, so the entire product evaluates to 0. So the clause polynomial will get the value 1, and of course if every single literal is unsatisfied, then this product is all ones, meaning that we get 1 minus 1 and the value 0 out. Now it's actually important to start paying attention to the degree. So what is the degree of this polynomial, where by degree I mean a sum of the degrees in a monomial, the individual variable degrees in a monomial. And again, we can check in the literal case, so if I go back one slide, here that this has degree 1. So it's basically a linear polynomial always. Now if you think about how does the closed polynomial look, so it's a product of linear polynomials, so basically as many polynomials as we have literals in the clause, and of course there are in total at most, or in fact exactly 2 times n literals, I mean 1 positive literal for each variable, 1 negative literal for each variable, there are n variables, so then actually this polynomial has degree at most 2n. Of course, sorry?
It just says it must end.
Well, yeah, of course, if you want to simplify your instance beforehand, but I mean, it doesn't really matter. We can be sloppy here. So, yes, you could trim it a little bit, but this is being sort of super loose with the bounds. This is a correct statement. Okay, fair enough. So now we have this wonderful property that if I have a satisfying assignment for a clause, I get the value 1 out. Otherwise, I get the value 0 out. So a standard algebraization of this multivariate polynomial. So finally, let's go to the collection of clauses, where we, of course, take the product of the closed polynomials in the collection. And of course, that is satisfied if and only if we get the value 1 out of the polynomial, or otherwise we get the value 0. So this is fantastic. So we can actually use this polynomial to start counting satisfying assignments. However, let's not worry about the computational complexity yet at all. Let's just observe that this thing, obviously since each of these component polynomials was of degree at most 2n, and here we are taking a product of m of them, so the total degree is upper bounded for sure by 2 times m times n. Again, it's a conservative upper bound, but that is how it is. Okay, so far so good. So now let's...
Do we later will need the book has such a degree because all these values xi takes values 0 and 1, and you can sort of trim off something.
Yes, but notice that we are actually working over a field. So you're asking a very good question. We want to actually retain sort of the entire field. So it actually working over this field with Q elements is important. You will see soon why. So yes, let's say if we were working actually in the Boolean case, so then of course we could trim it down and you wouldn't need to look at such high degrees and whatnot. But bear with me, so there is a reason why we sort of do it this way. And I realize that the bounds are loose, but they will suffice to get to our objective. Okay, so let's sort of summarize what we have now. Again, we are working over a field that contains 0 and 1. We have n determinants, we have a collection of clauses, and we have this polynomial that basically indicates for a 0, 1 valued assignment to the polynomial whether the assignment is actually satisfying, indicated with the value 1, or whether it's not satisfying, indicated with the value 0. So if we want to study again, so Q is our favorite prime, which we will eventually select, not yet. So we can actually get, by summing this polynomial over 0, 1 assignments, all 2 to the n of them, actually the number of solutions modulo Q. Okay, again, sort of perfectly straightforward elementary fact. So I'm stating the obvious more or less. Okay, and of course, if I have access to basically this value modulo Q for sufficiently many co-prime moduli Q, then I can actually recover the exact value here. So this in principle is somehow a sufficient building block to start getting into a good proof system. However, let's not yet worry about the computational aspects. So now let's actually get into more technical stuff already. I start worrying about the computation a little bit. So how do we actually do these things? And actually this slide is again maybe the most important slide in the lecture, so we will spend some time on this. So now we go from multivariate to univariate and then start seeing what's going on. So this takes some time. Okay, again we can sort of by standard reductions assume that n is even. N was the number of variables. And again, with a little bit of foresight, so let's actually choose the prime q so that it's in this particular interval. So m was the number of clauses and n was the number of variables. So again, you see there's basically this constant time, or I mean this quantity times 2 is here. So again, by standard facts about prime numbers, so we know that there are prime numbers in this interval. So let's just find one, basically starting with essentially, I don't know, brute force search or whatnot, and we know that primality testing is in P, so we can actually happily construct, let's say, 2 such primes in this time. You can sort of check if that, I mean, checking each prime is sort of relatively cheap, and you have an exponential amount of running time, so you can happily go over the possibilities like that. So it can be done. Okay. So we have those 2 primes, Q1 and Q2, so let's keep that in memory. And now let's start using actually the univariate toolkit that we have. So notice that what I want to do is, so I want to build univariate polynomials with coefficients in the finite field, so I can modulo Q, where Q is a prime, whose degree is at most 2 to the n over 2 minus 1. So we're actually constructing interpolating polynomials. And what precisely are we interpolating? So notice that in total I want n over 2 polynomials. So you should think of this that for each coordinate actually I want a polynomial. Coordinates of what? Notice here on the left hand side, what do I have? The set of all binary strings of length n over 2. So each string has n over 2 coordinates. Okay, and there are lots of strings, 2 to the n over 2 of them. So for each coordinate, I want a polynomial. Okay? And what that polynomial is supposed to do is to actually interpolate precisely that coordinate. So notice on the right-hand side, I again have a set, right? So what is this set? So it's a set of evaluations of these n over 2 polynomials at each index alpha. And notice that alpha now just ranges over 2 to the n over 2 integer values. And notice our field size is large enough to actually contain these distinct integers. And what I want these polynomials to do is to just interpolate the coordinates. So if you want, let's say, let's list this in lexicographic order and consider the most significant coordinate. So then, for example, this polynomial would just interpolate things so that in the first 2 to the, n over 2 minus 1 in the exponent, you would have a 0, and then in the rest a 1, and so forth. I mean, so these things just do nothing but interpolate the coordinate values. And again, now we have the fantastic toolkit of fast interpolation. So with this amount of resources, we can build these polynomials. That's it, we have them. Okay, so now let's define a univariate polynomial. And notice now, I mean, we had this lowercase multivariate polynomial that, I mean, over 0, 1 assignments was basically counting us or indicating to us whether we have a solution to the instance or not. I mean, of this collection of clauses, curly C. Okay, so, but now we have a univariate polynomial in a single indeterminate x. Okay? So how is that polynomial defined? Notice I do a little bit of work here. So this is an exponential sized sum. In fact, this sum, if you think about it, I have n over 2 variables, each taking values in 0, 1. So this sum contains 2 to the n over 2 terms, where again the n over 2 is in the exponent. And what am I summing? So what is each term like? Let's see. So I'm actually putting in these values explicitly into the polynomial. I mean, this is an n-variate polynomial, if you remember. So these n over 2 values go explicitly in there. And then I'm using this interpolation or interpolated polynomials. I'm just substituting there. Okay? And
so on the left you have capital P and on the right you have
lowercase p here. Yeah, this is the multivariate polynomial, and this is the sort of, maybe the capital P indicates that it might have something to do with the virtual proof. Maybe I should have sort of baptized it pi, but I mean, it's still p because pi needs a little bit more. But we're almost there. Okay, so now let's worry a little bit about degrees and such things and start thinking about computability eventually. But notice that, I mean, we can construct these A polynomials explicitly because we have the tool. So we can build this in coefficient form, we can batch evaluate them, we can do basically all the tricks we want using the fast toolkit. So, okay, so let's recall the definition of the capital P polynomial from the previous slide, just for convenience. And now let's carefully analyze. So this is a univariate polynomial. Basically, it's in the variable x. So what is an upper bound on its degree? So let's try to calculate this carefully. So first, let's recall what was the degree of the multivariate polynomial, because this, of course, affects our substitutions. So let's go back to recall this. Where do we have it? We have it here. Yeah. Yeah, 2 times m times n, so that's the naive upper bound. Okay, so fair enough. So let's now go in here and let's think about how. Sorry, I mean over here. How does degree behave under substitution? So if you think about, there is a multiplicative dependence. So 2 times n times m, and now I'm sticking in sort of to the first n over 2 variables some relatively high degree polynomials. But how high a degree precisely? Let's check this from the previous slide. So the degree is at most this, 2 to the n over 2 minus 1. Okay, so we go to the next slide and we see 2 times m times n, so the plus 1 is there, and then we have the n over 2. Okay, and we were actually very careful to choose our field size so that this degree here is upper bounded by half the field size. Of course, this need not be an exact division, but I mean, it's nevertheless that inequality holds. Okay, so in fact, we have a relatively low degree polynomial now in the grand scheme of things, because remember, we have a near linear time toolkit. So in the degree of the polynomial, we can do many, many things, and the degree is way, way less than 2 to the n. It is 2 to the n over 2, but we are in business because I mean, we have near linear time tools for coping with this. So here is one thing that, again, I want you to take a little bit of contact to this material. So I'm just saying that there is an algorithm, actually, that given your favorite collection of clauses, whatever that may be, m clauses over n variables, and a point in the chosen finite field where q is one of the primes, either q1 or q2. We don't really care as long as it's in the interval that we specified. So what I claimed is that we can compute the value of this polynomial in this running time, actually sort of counting all the bit complexity. So this is really now no longer counting arithmetic operations, but actually all the bit complexity of arithmetic. Okay. So think about it. We have a low degree polynomial whose values we can access in this time individually. Okay. So let's hold that in mind and just observe that by construction, again, recall how this was defined. So we have this interpolating polynomials controlled by x. So the interpolating polynomials were a1 through an over 2, and then we have this summation. So again, if we stare at how those interpolating polynomials were defined, if I actually take the sum over the first 2 to the n over 2 non-negative integers, and I sum these values, again, or evaluate the polynomial at alpha, I actually get the correct count, modulo q. But again, if I have multiple primes, so I can actually recover the correct count. So let's keep that also in mind and think about it. So if we had this polynomial in coefficient form, for example, so how much resources would it take to actually compute this? So what is this task that we are doing? Well, we are evaluating the polynomial over and over and over again at distinct points, but this is called batch evaluation. Okay, so we have a polynomial consisting of at most this many coefficients, basically, and we want 2 to the n over 2 points again, so the overall complexity is 2 to the n over 2. So if we had these things in coefficient form, we could actually recover n, because all it takes is those 2 primes, and sort of then we use Chinese remaindering, and we would be done. So this is sort of mighty nice. Now we almost have the ingredients in place, if you think about it. So how could we actually prepare this polynomial now? So let's first sort of think about that. So again, assuming, I mean, this is an exercise for you, so you'd actually need to build the evaluation algorithm that gets the job done. But I could, if I had the time, sort of consider each of these points xi individually, so that let's say pick the first at most this many non-negative integers, and I actually, sorry.
I ask you about
yes.
this exercise? So is it like straightforward to compute it?
Yes, yeah, but it's a little bit, again, you need to be careful. It's straightforward, but because again, I mean, obviously you have access to these polynomials, and then you need to, but again, remember that you're not working over 0, 1 values. So the catch is that this may be any element in the field. So we are working over potentially something that is not 0, 1 valued. So you feed to your interpolating polynomials something that is not in this range, that it would produce 0, 1 values. But again, since everything is defined in terms of polynomials, of course the calculations extend to the field.
Yeah.
But still, it takes a bit of concentration and careful effort to complete it. It's not difficult by any means. Mm-hmm. But again, I want to leave it to you so that you really sort of get in contact with the material. So sorry to be a little bit evil, but I mean, it's one of these things that you need to be careful. And if you, for example, want to do some further research in this area, so then it's a good idea to really get acquainted with all the nuances. So that's why I'm sort of with sort of loving intent being a bit evil. Okay, fair enough. So let's see. So indeed we have access, again we were here, so to the evaluation algorithm. So we can actually produce about, I mean, at least this many evaluations at distinct points. So then of course, I can interpolate the polynomial in coefficient form, and once I have access to the coefficient form, I can batch evaluate happily, and then I can recover n. So proof preparation. So how much time does it take? Well, we need this many points, and each point costs this running time. So again, sort of 2 to the n for proof preparation.
So once again, what is a proof in this case?
I will define it in more detail, but for example, you could say that it's just this polynomial in coefficient form for the 2 primes that you have chosen. That suffices.
I see.
Yeah, because if you think about it, so how many coefficients do I have? So at most this many plus 1.
Right.
So in each polynomial, and I needed sort of the calculation for 2 primes. So again, the proof size is small. Of course, each coefficient comes from the field, but it's still, I mean, the field elements don't need too many bits. Right. Because again, remember what the prime size was. So this is basically about n bits, plus some logs there, but I mean, not too much.
Yeah.
So the field elements are sort of hidden by the star, if you want. Okay, so proof preparation in the form of actually the coefficients of the polynomial costs you order 2 to the n work, which is nice. It's sort of the same order of magnitude in terms of the exponential growth as just solving the problem with the best known algorithm. Of course, there might be something better out there, but that's the state of the art currently. Okay, good. And I, of course, strongly recommend solving this exercise, and then you know what's going on, really, that you sort of write the detailed pseudocode, what is happening. That first you actually construct these polynomials, and then you start using them. So it's sort of basically like that. Okay, good. Let me see. Okay, so here is in a little bit more detail what is the proof string, if you want. So what is precisely pi? So again, so for large enough n, we can assume that there is such a such a prime. There are in fact two of them. And given the set of clauses, I mean, again, we can produce, let's say, E evaluations at distinct points. And if basically we have sufficiently many points, as we already argued, so that was the count, we can actually interpolate the coefficients of the polynomial. So then, of course, if you think about the prime Q and the coefficients of the polynomial, because of this degree bound, so we can, for example, use a prefix coding to basically overall get a bit string that depends on the prime of this length. I mean, upper bounded by that quantity. And then, of course, I mean, we can choose those two primes so as to enable recovery using the Chinese remainder theorem as already discussed. And then the actual proof thing pi is just a concatenation of these two guys.
We have the polynomial and we compute the on several points, or?
The polynomial is actually constructed explicitly only in the end. So notice that we have access to the polynomial, but it is costly. So each point evaluation costs you basically an exponential amount of resources. Yeah. And you need many of these evaluations to actually get the polynomial so that you can recover the coefficient representation. In fact, you need about 2 to the n over 2 evaluations, each of which costs this. But the proof itself is small.
For fixed point.
Yeah, it's for a fixed point. An individual evaluation costs this. But of course, you can run this over and over again at distinct points.
But can we do batch evaluation?
Of course not, because we don't have access to the polynomial yet in coefficient form. That's what we want to recover.
Okay, then what do we have to do?
I mean, there are two things. So first is preparing the proof. I haven't yet told you how you check it.
I don't understand how the proof is.
Assuming that you don't have the polynomial only the oracle access to it.
Yeah, you have a black box that gives you the polynomial's value at point xi, and the black box costs you this much. So to recover the polynomial, because we know an upper bound on its degree, namely here, I can of course run the black box at sufficiently many distinct points so that then I can actually use interpolation, fast interpolation, to recover the polynomial. Then I have the polynomial in explicit coefficient form, not before that.
But it takes 2 to the n.
Yeah, that's proof preparation time. Remember, I'm not yet talking about verification. Okay. So we're just thinking about proof preparation, and then let's think about verification. And that's actually where we will use the fact that we are working over a large field. Okay, so.
But why we need 2 primes to 1 P2?
Again, look at the size of the primes. You want to recover potentially a count as high as 2 to the n. Because remember,
the n could be as much as
2 to the n, yes.
Okay.
Again, because remember, where are we? So here, I mean, n can be, of course, I mean, the formula may have 2 to the n satisfying assignments, and you only get the count modulo q. So to actually get the exact count, you need 2 primes, in the interval that we. So again, if you think about it, if I take this squared, so it's at least 2 to the n. So it suffices. Okay, good questions again. So sorry to maybe present this in a little bit out of order fashion. So there are many storylines interleaved.
So
yes?
Could you tell me why don't you just use 1q, which is like greater than 2 to the n?
Let's think about this. So what would actually change? That's a very good question. Do you see why this is needed?
Yeah, I believe that it is needed somewhere. But
Yes. Look at this part.
right.
So we actually
I see.
need to
I see.
find these primes, for example, for proof preparation, and also for checking. Of course, you can just run a primality test, but yeah.
But if like someone give us q for free.
Yeah, but even then, I mean, okay, so if someone actually gave us q for free, so then I could just deal with a single prime, but it wouldn't affect the argument greatly. It's just that here I've sort of been careful that I mean, again, to run the evaluation algorithm, I mean, just to get a single point evaluation, I want to be in this time envelope. And of course, part of this point evaluation is that you actually choose the smallest prime in this interval. And now the time budget is actually sufficient to do this. You can start a brute force search that starts from this number, whatever it is. Of course, it's a composite, but then sort of war dials through the candidate primes and sort of finds the first two. And it all can be built into the evaluation algorithm. Because remember, actually here, I mean, for the evaluation algorithm, you need to have access to the field. You cannot otherwise compute. So to gain that access, it sort of makes sense to have those two primes, and then you need to be able to find them within the allocated time budget.
So, like, if someone gave us Q, why should like,
yes, yeah, then of course you can check that it's prime, but again, I don't want to make such assumptions. I want the algorithm run as a standalone. I don't want any kind of oracle knowledge of, but if somebody gave us the Q, of course, then the Q can be large enough and then we are happy. So then we don't need two primes. Yeah, sure, of course. Yeah. But again, making such an assumption would be a sort of beauty defect. Okay, very good. Okay, right, so we looked at the proof string. So again, two primes and the associated polynomials will sort of suffice. But now let's actually think about the soundness. So, okay, first, of course, completeness. So yeah, sure, it spells out the argument that once we have those things, since the product of the two primes is at least this, we can use Chinese remaindering to recover things. And again, we can use batch evaluation to sum up the number of assignments there. So that's basically it. So in the sense, the verifier will always accept the correct triple in the claimed running time. Okay? But how about the soundness?
So could you probably elaborate more on what it takes to accept? So if I need to accept a string as a verifier, what do I need to?
Yeah. So this is just, I mean, if you really have the correct proof, but we still need to check actually that we have the correct proof. And this is coming on the next slide, if you bear with me.
Can you have a break?
Oh, absolutely, yes. Okay, right, so we have the proof string as sort of depicted here. So it consists of basically the two primes, Q1 and Q2. And then, I mean, together with the prime, we actually represent the coefficients of this polynomial modulo the chosen prime. And we need the two primes so as to be able to recover the count of satisfying assignments modulo, I mean, at least 2 to the n, more than 2 to the n, using the Chinese remainder theorem so that we sort of can sort of convince ourselves, given a correct proof, that things are good. But we haven't yet discussed how to actually check the proofs, because of course the verifier needs to reject with high probability whenever it gets a bad proof, however that bad proof is formatted. So that part is not yet clear at all how to do this. But let's just sort of quickly recall the completeness first. So if we are given the correct proof string, of course we can assume that it's correctly formatted and whatnot. So we can sort of pick up the primes and then just use batch evaluation on the polynomial at the relevant integer points so as to actually recover the evaluations. We sum them up, modulo the relevant primes, and then use the Chinese remainder theorem to actually reconstruct n. And then we have the correct count. Again, assuming, of course, that we have the correct polynomials. And all of this takes time order 2 to the n over 2. So about square root of the sort of best known solution time, if you want. But now yes.
We do not need to, as a verifier, we do not need to check the polynomials are correct.
We do, yes. In this case, when checking completeness, we assume that we have a good prover. But of course, now we need to check soundness. So we need to do some further checks to really make sure that we got the real deal and not some bogus polynomial, for example. And this we haven't looked at it at all. So now we need to be careful and actually stare at sort of that we can catch a bad prover in action with high probability. So let's get to that point now. So let's analyze soundness. So let's review the setup. So what checks do we need to perform on the proof string? And now notice that we really get a pi tilde and we get some n tilde, which may not be the correct count. It's just something that we get submitted. Of course, first we look at what we get. So we apparently get some kind of integer and then something that seems to encode a polynomial. I mean, those two primes we get, and we can of course check them for primality. So that much we can sort of obviously check. So basically it's a concatenation for those two primes as claimed, and then that these things actually encode the coefficients of a polynomial of at most this degree and so forth. So these are just sort of straightforward bit encoding checks that the input is correctly formatted, but then we need to actually verify we can of course verify the primes as well if we want that they are actually the two least primes in the interval, again because of the time complexity that we have, order 2 to the n over 2. The primes are exactly so large that we can even check them if we want. But now the hard part is that we sort of get this. So I mean, let's say that p tilde now refers to one of the primes. Okay, either q1 or q2. Let's not worry about that too much. So it's q, if you will, that we are touching. So this is what we want to check, that p tilde is the correct polynomial. So remember, this by definition is what we want, but the sort of prover may submit to us whatever. So we need to be a little bit careful. So we actually do a randomized test. So we repeat the base 2 logarithm of n rounded up plus 1 times the following thing. We pick from the field, I mean independently of course in each iteration and uniformly at random, an element xi. And then what we do is that we test that this identity holds. That basically the correct polynomial evaluated at xi equals the polynomial that the prover submitted to us, whatever that may be. Okay, so let's see that we can actually do this computation, that we can evaluate both the left-hand side and the right-hand side. We get two scalars, and then we test them for equality. But let's first check that both left and right-hand side are accessible. So how do we access the left-hand side? Well, I mean, we are given the polynomial very kindly to the prover gave it to us in coefficient form. So what is the degree? It's about this much. So using Horner's rule, again in the allocated time, namely this time, we are happy to oblige. So this side can certainly be obtained. Okay? So how about the right-hand side? So we are supposed to evaluate the correct polynomial. Well, as it turns out, of course, since we are verifying a proof, we have access to the problem instance. So we have access to the clauses and whatnot. And remember, we had this evaluation algorithm. So let's go back a couple of slides. So what were the properties of the evaluation algorithm, whose details I, in an evil way, left as an exercise to you. So you see, given any point xi, we can actually produce a value of the correct polynomial in the allocated time. So we can actually also produce the other side of the equality, or the claimed equality, obviously. So let's go here. So this can be produced also within the relevant time budget. Okay, and then of course, I mean, yeah, if we get inequality here, I mean that equality doesn't hold, then we know that the prover is not in good shape, so we reject immediately. And then of course it may be the case that all of these tests pass. But remember, we are using randomness here. So what is the probability that all the tests will go through? This logarithmic number of repetitions in the number of variables. So now, of course, we get into polynomial identity testing. So let's try to analyze the parameters. So here we are. So again, so really suppose that we don't have the correct polynomial, namely that this difference is not the zero polynomial. Well, let's look at the degrees of these two polynomials. So what is the degree of p tilde? Again, we have control on this because this was submitted to us by the prover, and we did check that its degree is no higher than this. Okay, so fair enough. And then we also know by construction. So we were very careful to construct this proof polynomial as a univariate polynomial so that its degree is bounded again by this quantity. So both components of this difference have degree bounded by this quantity, meaning of course the difference has degree bounded by that quantity as well. So it's a manifestly low degree polynomial. I mean, comparing with the field size, so we were again very careful to choose the primes in such a way that they are at least this large. So basically, if you think about, so if we are unlucky, of course we basically hit the root of the difference polynomial with our random test, and then we sort of get equality in one of the tests, number of repetitions. Okay, is it good? Okay, very good. All right. So again, where were we? So we were very careful to make a logarithmic number of repetitions. So what's the probability that an individual repeat actually witnesses a failure? So not witnessing means hitting a root of the difference. But the degree is this, so there are at most half the field size roots, and the rest have to be non-roots. So with probability at least 1/2, I'm going to hit a non-root, thereby catching the bogus prover in the act. And then of course, I mean, I repeat a logarithmic number of times in the number of variables, independent repetitions, so this is basically the probability with which at least I will catch the prover after those repetitions. Again, I mean, you can check the details, it's an easy exercise. So this is all there is. Because we have access to the point evaluation algorithm and we are talking about low degree polynomials, so we are in good shape. So there's basically nothing that the prover can do to avoid getting caught with high probability. So, and the verifier all in all actually runs in the square root of the sort of fastest known algorithm to actually even just decide the problem. Okay, so that's nice. Any questions? Yes?
Where we use the number of solutions.
I mean, okay, so once you know that you have the correct polynomial, then you can actually recover the correct number of solutions. And whatever is being claimed, you can check for equality. Remember, this you can recover as soon as you have the correct polynomials.
We just calculate this.
Yeah, you can use batch evaluation to get it. Yeah, okay, good question. All right, so now I think we are sort of done. So we have a proof system with probabilistic soundness. Verification is substantially faster than solving the problem with the best known algorithm. Proof preparation is not too difficult either compared with the best known solution algorithm. And yeah, there are many things about this that we can like. Okay, yeah, fair enough. So this just sort of recalls what we have already covered and what I just said in words. So let's look at the tolerance for errors, actually. And let's start thinking actually how we could change this setting a little bit. So what did actually proof preparation involve? What was the idea? If you think about it. So what we did is we basically farmed a great deal of evaluations of a univariate polynomial. I'm sorry about the notation, so sort of this should be a capital P to be compatible with what we discussed, but now this is a little bit more a general setting. So what the proof preparation really amounts to is that you farm a lot of point evaluations of a univariate polynomial. So I mean, these are completely independent of each other. You can run them on separate computers, produce them. Some of these things may actually even be in error. Maybe you know, I mean, and of course in general you have some kind of control, you know what the degree should be at most. So there's an upper bound D on the degree. So what did we learn about univariate polynomials today? So you can over-provision the evaluation. So if you know that the degree is at most 10, so why don't do 1,000 evaluations? So if there are a few bad evaluations in the batch, I mean, who cares? You can still interpolate the polynomial. So in fact, we can tolerate this many errors. I mean, it's a Reed-Solomon code, what we are doing. So in fact, if you want to make a distributed proof preparation, so this is what you want to do. You farm the evaluations and then you collect them, and then you can actually, on your own, in a single computer, do the decoding. Because remember, every evaluation costs quite a bit of effort, but there are all in all not too many evaluations that you need. So maybe the number of evaluations is about square root of the total effort, again. And each polynomial evaluation takes a square root of effort. So that's somehow the idea. So then we can decode, and what's nice about the decoding is that we can also locate the errors, if any. So this sort of makes it a neat community protocol as well, that if there's somebody who is cheating and trying to submit something to the system, so you can catch them in the act. And furthermore, of course, once you have the alleged proof, so you can check that it's correct. And if it's not, you will, I mean, even if everybody is cheating, you will with high probability sort of know this. Of course, then you don't know who is cheating, but at least you know that something is wrong, and you don't probably want to somehow use that service provider anymore. And what is also nice that once the proof is there, so it's perfectly transferable. So again, the service provider can take it to the judge, and the judge can, with modest computational resources, check that indeed there is no solution, so please pay up. So, so indeed. And then the verification is indeed nothing but sort of checking that we have the correct polynomial with a few spot checks. And then this works because we can sort of use a large field. So compared with the size of the field, the degree of the polynomial is small, so it's unlikely that you hit a root. So that's sort of the basic idea in identity testing. So I mean, again, sort of to maybe show this picture again. So I mean, everybody knows the problem instance, and then you farm it in lots of parallel machines, evaluating at distinct points. You get the point evaluations back. So over here, you can run the decoder and check that you sort of got what was agreed on, and so forth. And of course, also in here, we can actually run the error correction algorithm and start debugging if we have some malfunctioning nodes or whatnot. So we can try to pinpoint where the errors actually happened and if there's a pattern and whatnot. So there are basically many things to like about such a system, but it's still unfortunate that it doesn't sort of quite capture universal computation yet. So we have for many rather expressive problems this type of setup, but not yet for universal computation. So that's basically it if we want to wrap up things. So what we looked at now is actually trying to deal with errors in computation that happen silently and don't announce themselves through proof systems, where actually we are also paying attention to the act of preparing the proof and the cost of verifying it. So what we are sacrificing, of course, is the soundness, but we are not sacrificing too much because we can actually control the error probability after the proof has been prepared, if you think about carefully. So why is this the case? We can control how many repetitions we make, and we have an upper bound on the degree. So of course we can increase the number of repetitions and control the error probability by that way. So that's also another nice feature of the system. Okay, so I think this about concludes lecture 5. So I do still have, as usual, the problem set that actually involves a few warm-up exercises on polynomial identity testing and testing a matrix product, sort of the usual things. But then there's also the evaluation algorithm for your enjoyment, that you actually get to design the algorithm. And here you have some hints as well. And then there's a fourth problem, which is, we study, for example, how to do delegation to multiple parties. But I leave that as a sort of thing that you may want to study as for yourself, sort of a bit of an extension of Shamir's secret sharing, but again, sort of maybe of interest. It's a nice little brain twister. Okay, but I think that's about it. So now, I mean, I only have some references here that I can quickly flash over, and then we are done. All right, so this is my last slide, so thanks a lot.
Thank you.